Assalamu alaikum. In the last class, we have discussed about the configurations of the gas turbine engine, and in this class, we are going to discuss the assumptions for the ideal cycle for the gas turbine cycle, that is the Brayton cycle. In the Brayton cycle, as we know, the process in the compression is assumed to be the isentropic. That is, there is no change in the entropy. If there is no change in the entropy, it means there is no friction. Of course, during the compression process, there is no heat addition or there is no heat removal. Only the work is done isentropically from state 1 to state 2. As a result, the final pressure of the gas is going to increase. Similarly, during the expansion process, when the expansion is done from state 3 to state 4 during the expansion in the turbine process, so during the expansion process, the enormous amount of the energy is being released that is going to drive the compressor, and also that is going to produce the net power output. And during the expansion, we are going to assume in the cycle that the expansion process is purely isentropic and reversible. That is, there is no change in increase in entropy, there is no change in the entropy, so delta S is assumed to be zero. The next is the change of the kinetic energy of the working fluid between the inlet and the outlet of the each component is negligible. So when we are going to deal with the land-based applications, the fresh air is going to enter into the compressor, and when it is going to leave the compressor, its initial kinetic energy is different from the exit, and the same is case for the turbine. During the entry level at the turbine, the enthalpy is converted in the kinetic energy. So the changes in the kinetic energy of the fluid element between inlet and the outlet for each of these components is assumed to be negligible. And the third is there are no pressure losses in inlet ducting, combustion chamber, heat exchanger, and the intercoolers, exhaust ducting, and ducting connecting the components. Of course, when you are going to deal with the compressor, there are the pressure losses associated because of the fluid friction, and the exhaust ducting is assumed to be negligible, and also there is a pressure loss in the combustion chamber. So all these pressure losses are taken into account as negligible. So during the cycle, we are going to assume the constant pressure heat addition is actually a process without the pressure loss. Similarly, the constant pressure heat reduction in the Brayton cycle is assumed to be the process without the pressure loss. The next assumption is the working fluid has same chemical composition throughout and has the same specific heat capacity. That is, during the combustion process, the Cp and Cv value and also the gamma value, even the molecular weight that is represented by R, all these are going to change because the chemical composition of the air is going to change, that is going to enter into the turbine. So for this cycle, we are going to assume that the changes in the gamma, the changes in the Cp and Cv value are assumed to be negligible. The next is mass flow rate of the gas is constant throughout the cycle. Of course, you know the mass flow rate of the air that is going to enter into the turbine is of course higher, because the air coming out from the combustion is going air coming out from the compressor is going to enter into the combustion chamber, and during the combustion chamber the fuel is being added. As a result, the mass flow rate of the air entering into the turbine is higher than the mass flow rate of the air entering into the compressor side. So as a result, we are going to assume that the mass flow rate of the gas is constant throughout the cycle. The next is heat transfer in the heat exchanger is maximum. The temperature raise at the cold side is equal to the temperature drop in the hot side. So if someone is going to employ a heat exchanger in the gas turbine cycle, he is going to assume that the effectiveness of the heat exchanger is maximum. That is the ratio of the actual heat transfer to the maximum possible heat transfer, and whatever the drop in the temperature in the hot side is equal to the gain in the temperature at the cold side. Okay, so now we have shown here a simple gas turbine cycle. As you can see here, the compressor draws the air from state 1, and during the combustion process the air is leaving the compressor at the state 2, and heat is being added in the combustion chamber from state 2 to state 3, and from state 3 the gas is going to enter into the turbine and it leaves out at the state 4. The turbine drives the compressor, and the rest of the expansion is done in the turbine to drive the generator. Okay, and this is the cycle. As you can see here, from state 1 to state 2 this is isentropic compression, and from state 2 to state 3 this is a constant pressure heat addition, and from state 3 to state 4, as you can see, this is a vertical line for the expansion as well as for the compression. So from state 3 to state 4 this is isentropic expansion, and from state 4 to state 1, in order to complete the cycle we have introduced here the constant pressure heat rejection process. Okay, now we have shown here the R, which is the pressure ratio. This R, small r, is the pressure ratio, and it is the ratio of P2 by P1. Since P2 is equal to P3, so we can replace the pressure ratio in terms of the temperature. Okay, so P3 by P1 or P2 by P1, the pressure at the point 3 and the pressure at point 2 are equal. So we replace the pressure ratio in terms of the temperature from the isentropic expansion. If you recall, P2 by P1 raised to power gamma or gamma minus 1 is equal to T2 by T1. So we have replaced the pressure in terms of the temperature, that is T3 by T1 raised to power gamma or gamma minus 1. Now one of the important thing is, as you can see here from the cycle, the maximum possible temperature attainable in the cycle is at the state 3. So this is the maximum possible temperature. If you are going to increase this temperature, that is decided by the creep strength of the blade material, and we can say that defines the metallurgical limit. So if the temperature at the turbine inlet blades is higher and higher enough, the thermal efficiency is higher. So we can now introduce the cycle efficiency as the ratio of the net work output divided by the heat supply. So the net work output is actually the, as you can see here, from the difference of the enthalpy from state 3 to state 4. But a part of the expansion in the turbine is used to drive the compressor. Okay, so you can say here the power output produced by the turbine, that is Cp T3 minus T4 minus, this is the amount of the work consumed into the compressor, that is minus Cp T2 minus T1. If you take the difference of these two, this is the amount of the total work that is being produced in the turbine, and this is the amount of the work being consumed into the compressor. So if you take the difference of these two, so this will give you the net work output. Okay, that is going to drive the generator. And for the heat supplied, as you can see here, the quantity of the heat is being added into the combustion chamber from state 2 to state 3, and this is also represented from state 2 to state 3. Okay, so the thermal efficiency can be written in terms of the temperature, and if you are going to replace these temperature in terms of the pressure ratio, so we know that T2 by T1 is equal to P2 by P1. P2 by P1 is the pressure ratio, and that is represented by small r raised to power gamma minus 1 by gamma, and this is equal to T3 by T4, that is pressure ratio. Pressure ratio for the compression is equal to the pressure ratio for the expansion. Okay, so of course for the expansion this is represented by T3 by T4. Now where the pressure ratio is P2 by P1 is equal to R is equal to P3 by P4. Since P4 is equal to P1 and P3 is equal to P2, therefore R represents the pressure ratio. The cycle efficiency can be written as 1 minus 1 over pressure ratio raised to power gamma minus 1 by gamma. So from this expression you can see, higher the pressure ratio, higher the thermal efficiency. Lower the pressure ratio, lower the thermal efficiency. So if the cycle is such that you are going to have the higher pressure ratio. Higher pressure ratio means the state 2 will be located at a higher point, and if the state 2 is located at the high pressure point, let's say here, then the maximum cycle temperature will also become higher, but that is limited by the strength of the turbine blades that can sustain that high temperature. So there is a limit to the pressure ratio always. So depending upon the strength of the material that the turbine blades can sustain high temperature, the pressure ratio in the cycle can be decided. So this is the curve of the efficiency versus the pressure ratio. As you can see, on the y-axis we have plotted the efficiency, and on the x-axis we have the pressure ratio. So increasing the pressure ratio is going to increase the efficiency of the system. Okay. So this is the gamma is equal to 1.4 for the air, and this gamma is equal to 1.666. The air becomes less compressible as the gamma is going to increase. Specific work output can be written as the power produced in the turbine minus the power consumed into the compressor. So the difference of these two will give you the net amount of the power or the work which is to be produced by the turbine during the expansion process. Okay, so we can write it in such a way that we divide the whole equation by T1. So we have T3 by T1 and T4 by T1 minus Cp, T2 by T1 minus 1. Okay, and we are going to replace this T3 by T1 in terms of small t. Okay, now we take Cp as a common, and we have taken out the W net divided by Cp times T1. This left hand side equals to small t is taken common from this equation. So you are left with 1 minus T4 by T1 times 1 over T bracket close minus T2 by T1 minus 1. Okay. Now we want to put the value of small t, which is T3 by T1. Okay. So this is 1 over T. So this will become T1 by T3. So small t 1 minus T4 by T1. T1 T1 now get cancelled out, and the remaining expressions are same. Now we want to express this temperature ratio in terms of the pressure ratio. So T4 by T3 becomes P4 by P3 raised to power gamma minus 1 by gamma, and T2 by T1 becomes equal to P2 by P1 raised to power gamma minus 1 by gamma. Okay. Now we want to express this pressure ratio in terms of the gamma. So W net by CPT1 will become equal to small t multiplied by 1 minus 1 over pressure ratio raised to power gamma minus 1 by gamma minus pressure ratio raised to power gamma minus 1 by gamma minus 1. Okay. Now we need to find out what is the point at which this net work done become equal to 0. So this net work done become equal to 0 when you have the pressure ratio is equal to 1. Okay, so if you have the pressure ratio is equal to 1, it means there is no compression in the compressor side and no expansion in the expansion side, such that the pressure P3 is equal to P4 and P2 is equal to P1. So in that situation, there is no net work done by the cycle, and also the net work done is also equal to 0 when the work of the compression is equal to the work of the expansion. When these compression and the expansion process are going to coincide at a particular point, then we can say the net work done is equal to 0, and this becomes 0 at the value of the gamma is equal to T raised to power gamma over gamma minus 1. Now remember, this gamma is the pressure ratio, and this small gamma is equal to specific heat ratio, that is Cp by Cv. TS diagram where the work W net become equal to 0. So it is equal to 0 when you have the pressure ratio is equal to 1, and also it becomes equal to 0 when the work of the compression coincides with the work of the expansion. Okay, so in that situation we have the pressure ratio is equal to T raised to power gamma or gamma minus 1, and this small t is a function of T3 by T1. Okay, now if we are interested in finding out what is the maximum value of the net work output that is given by the cycle, we need to have we have to differentiate this equation with respect to gamma raised to power gamma minus 1 by gamma. Okay, and equate this equation to become equal to 0, and then finally you will find the optimum value for the pressure ratio, which is equal to gamma optimum raised to power gamma minus 1 by gamma is equal to under root of t. Okay, so if you are going to square the two sides, you will get gamma raised to power 2 gamma minus 1 by gamma is equal to t. Solving this expression, t can be replaced by t3 by t1, and gamma raised to power 2 gamma minus 1 can be written in this form. We can multiply both the equation, so if you are going to add the equation, the power will be added. Okay, now we are going to replace this gamma in terms of the pressure ratio, and this pressure ratio can be replaced in terms of the temperature ratio. So this P3 by P4 can be replaced as T3 by T4, and this P2 by P1 can be replaced as T2 by T1. Now cancelling the similar terms, T3 T3 is cancelled out, T1 and T1 are cancelled out, so you are left with T2 is equal to T4, which shows that the T2 is the temperature of the gases or the air. T2 is the temperature of the air coming out from the compressor, and T4 is the temperature at the outlet of the turbine. So if the temperature of the air leaving the compressor is equal to the temperature of the gases leaving the turbine are equal, then in that case we have the specific work output will have the maximum value. For all the values of the gamma between 1 and t raised to power gamma over 2 gamma minus 1, T4 will have greater than T2. So if you have the value of the gamma even higher than t raised to power gamma over 2 gamma minus 1, then the T4, the gases which are coming out from the turbine side, instead of providing heat to the incoming air by means of the heat exchanger, they will become cooled down. So this is the curve of the specific work output versus the pressure ratio. As you can see here on the x-axis we have plotted the pressure ratio, and on the y-axis we have plotted the specific work output. As you can see here, when you are going to increase the pressure ratio, the specific work output increases first, and when the pressure ratio is going to increase further and further, the specific work output decreases. As you are going to increase the value of the maximum cycle temperature, the specific work output increases also. As you are going to decrease the cycle temperature further and further down from T5 to T2, then the specific work output also decrease. Okay, but remember, one of the important thing is up to a particular value of the pressure ratio, the specific work output increases. A further increase in the pressure ratio will decrease the specific work output. Initially we have the simple gas turbine cycle, and now we are going to deal with the heat exchange cycle. In the type of the heat exchange cycle, as you can see here, the air that is drawn from the compressor at the state 1 leaves out at the state 2, and this is going to extend the heat with the exhaust gases of the turbine that is coming out at the state 4. So the exhaust gases that are coming out at the state 4 are at a higher temperature, as you can see here, and these are going to exchange heat with the cold air that is leaving out from the compressor at the state 2. Okay, so instead of burning the fuel from state 2 to state 3 directly, the temperature range from 2 to 5 is taken into account into the heat exchanger. So this quantity of the fuel which is to be burnt in raising the temperature from state 2 to state 3 directly has now saved by mean of the heat exchanger. As a result, the temperature of the gases has increased from state 2 to state 5, and only in order to increase the temperature from state 5 to state 3 we need to incorporate a heat exchanger. Okay, so once the temperature has fallen from state 4 to state 6, no further heat exchange is possible because the temperature of the hot air that is leaving out the heat exchanger at the state 6 is now become equal to the temperature of the incoming air that is leaving out from the compressor. So the temperature of the incoming and the outgoing fluids are now equal, so there is no more heat exchange possible. Okay, so the effectiveness or the efficiency of the heat exchanger in this cycle is of important concern. Okay, by introduction of the heat exchanger one can have the higher efficiency because the quantity of the fuel supplied in the heat exchange cycle is now reduced. So the gases has to increase its temperature only from state 5 to state 3 instead of increasing instead of increasing the temperature from state 2 to state 3. So now we can write the efficiency as the net work output divided by the heat supplied. Previously we have the heat supplied from state 2 to state 3, and now for the case of the heat exchange cycle we have the heat supplied from state 3 to state 5. Okay, assuming the CP to become same, so we can write the efficiency as efficiency for the heat exchange cycle will come out to be 1 minus pressure ratio raised to power gamma minus 1 by gamma divided by T. Now this efficiency, as you can see here, if I increase the value of the T, that is the maximum cycle temperature, the small t is equal to T3 by T1. Okay, so if you are going to increase the small t, the maximum cycle temperature T3 is going to increase. So if the T is going to increase, the efficiency becomes higher and higher enough. And if the compression ratio is decreased, efficiency is also higher. But in the case of the simple gas turbine cycle, if you have noted, by increasing the pressure ratio, efficiency increases. But now this time, if you are going to increase the pressure ratio, the efficiency has to decrease. Or if you are going to increase the cycle temperature, maximum cycle temperature, that is T3 by T1, then the efficiency has to increase because it appears in the denominator. Okay, so 1 minus this pressure ratio raised to power gamma minus 1 by gamma divided by T. Now let's look at the curve of the efficiency for the simple gas cycle with heat exchange. So this dotted line curve is shown for the simple gas turbine cycle without the heat exchange, and these curvature lines of constant T family are going to represent the curve of the efficiency versus the pressure ratio. As you can see here, with increasing pressure ratio, efficiency drops, and for the higher values of the T, the curve of the constant T line is located, and the curve of the constant T line for the lower values of the T is located at the below side. Okay, so I hope the concept is clear now. Now remember, the specific work output will remain same in the case of the heat exchange cycle as we have seen the specific work output for the simple gas cycle. So there's no increase in the specific work output because the area under the TS diagram has not increased. If you are going to increase the area under the TS diagram, then the area under the TS diagram shows that the work done. So if the area under the TS diagram, as you can see here in this case, is going to increase, then only we can say the specific work output increase. But a simple gas turbine cycle with a heat exchanger will not increase the specific work output, although it will only increase the thermal efficiency. So in order to have the higher specific work output, we need to have the reheat cycle. As we can see here, the reheating is done into the stages. So the high pressure turbine have the expansion from state 3 to state 4, and we have the expansion from the state 5 to state 6 in the low pressure turbine. Since the thermal efficiency of the reheat cycle is actually lower than the thermal efficiency of the simple cycle, because for the simple cycle the gases are going to expand in the turbine from state 3 to state 4. Okay, so this is the higher pressure, the expansion is going to done at the higher pressure from state 3 to state 4, whereas in the case of the expansion, when it's to be done into the stages from state 4 to state 5, when the heat is being added at the low pressure and the expansion is done in the low pressure turbine, this low pressure cycle imposes upper limit on the thermal efficiency. So as a result, the thermal efficiency of the reheat cycle is actually lower than the thermal efficiency of the simple gas turbine cycle. And the specific work output can be given as 2T minus C plus 1 minus 2T by under root C, where C is equal to pressure ratio raised to power gamma minus 1 by gamma. Similarly, we can write the expression of the efficiency, which is 2T minus C plus 1 minus 2T divided by under root C divided by 2T minus C minus T divided by under root C. Okay. Now the expression of the thermal efficiency can be obtained if you are going to write the expression of the thermal efficiency as the net specific work output divided by the heat supplied. Okay, so you can replace the net work output will be equal to this work output produced by the turbine minus the amount of the work that is being consumed into the compressor. So finally you will reach the efficiency expression in terms of maximum cycle temperature and the pressure ratio. So we have plotted the efficiency curve for the reheat cycle. As you can see here, the efficiency curve for the reheat cycle is slightly lower than the efficiency curve for the simple cycle. Okay, for the simple cycle the expansion is being done in the high pressure, whereas for the reheat cycle the expansion is done into the stages. As a result, this will increase the specific work output, but it imposes an upper limit on the thermal efficiency. Okay, as a result, because of the expansion at the low pressure, the thermal efficiency of the reheat cycle is actually lower. Okay, and for the different values of the T, the different plots of the pressure ratio versus the efficiency are given here. And if you look at the curve for the specific work output versus the pressure ratio, so at the higher values of the cycle temperature the curve appears to be higher, and for the lower values of the cycle temperature the curve appears to be lower. But as compared to the simple gas turbine cycle without the reheat, the specific work output has now increased because the area under the TS diagram has now increased. Okay. Now this is the cycle with reheat and heat exchanger. Now we can have the higher thermal efficiency with heat exchange, and we can have the higher specific work output with the help of the reheat cycle. So together these two things will not only increase the thermal efficiency of the cycle but will also improve the specific work output. Okay, so the simplicity of the gas turbine cycle is now lost because we have added multiple components, that is the reheater and a heat exchanger, that are going to increase the cost of the system also. But on the other hand, we have the higher thermal efficiency and we have the higher specific work output. Okay, so as you can see here, the air is drawn into the compressor from state 1, leaves out at the state 2, and when it leaves out, it enters into the heat exchanger that exchange heat with the gases leaving out from the turbine at the state 6, and finally the air coming out from the heat exchanger at the state 7 enters into the combustion chamber where it is to be burned, and its temperature is increased up to the state 3, and it is expanded into the HP turbine that is going to drive the compressor. And finally the rest of the expansion is done in the reheat in the low pressure turbine by means of the reheating the gases up to the state 5, and during this reheating the specific work output increases. So this is a TS diagram is shown here, as you can see here. From state 1 to state 2 we have the asymptotic compression, and from state 2 to state 7 we have the heat exchanger that is going to increase the thermal efficiency, as the amount of the fuel which is to be burnt into the combustion chamber in order to increase the temperature from state 2 to state 7 is now saved. As a result, we have the higher thermal efficiency because a very low quantity of the fuel is to be burnt into the combustion chamber and raising the temperature from state 7 to state 3. And from state 3 to state 4 we have the expansion in the high pressure turbine, and from state 4 to state 5 we have the reheating at the constant pressure, and from state 5 to state 6 we have the expansion in the low pressure turbine, and the gases coming out from the state 6 are going to exchange the heat with the air coming out from the compressor. So this is the curve for the thermal efficiency versus the pressure ratio. So this is the combination of the curves that we have discussed about the reheat cycle as well as for the heat exchanger cycle. So we have the higher thermal efficiency because the cycle has a heat exchanger, and also now the work of the compression that is actually higher, it can be reduced by means of the intercooling. Intercooling is actually done in between of these two compressors, so the raise of the temperature into the compressor actually increases the amount of the work of the compression. So to reduce the amount of the work of the compression, we have to reduce the amount of the temperature raise that is increased in the compression of the gases. During the compression, the specific volume decreases, whereas the density of the gases is going to increase. As a result, there is a net increase in the temperature. Apart from increase in the temperature, there is a small increase in the temperature has to be taken into account, and that increase in the temperature is going to increase the work of the compression in the next stages. So our effort is to decrease that temperature, thereby decreasing the work of the compression, so the cycle has the maximum efficiency and the minimum amount of the work loss. So in the last we are going to account for the losses that are taking in the component. The first one is the fluid velocities are higher in the turbo machinery components, therefore the changes in the kinetic energies are negligible. Of course we are going to deal with the turbo machinery component, that is the compressor and the turbine, that are going to have the number of the blades, and these blades are going to move at the faster speeds, so the changes in the fluid velocities is higher across these. So we are therefore going to neglect the changes in the kinetic energy. The second is compression and the expansion process are irreversible in adiabatic, therefore the entropy is going to increase. So since the compression and the expansion process in the real, these are going to increase the entropy of the working fluid. So as a result, we are going to account these processes as irreversible and the adiabatic. That is, they are going to be the non-isentropic process. The third is fluid friction increases pressure loss in the combustion chamber and in the heat exchanger and also in the ducting lines. So that is negligible. So that is going to take into account is the fluid friction that is going to increase the pressure loss in the combustion chamber as well as in the heat exchanger is now neglected. The fourth is because of the friction involved, the work delivered by the turbine will be slightly less than what is obtained and so for the compressor. So since the friction is present, so you are going to deal the whatever the amount of the work produced by the turbine is actually less and the amount of the work consumed by the compressor is actually higher. Okay. And also the Cp and gamma are changing because of the chemical composition of the gas throughout the gas turbine cycle is going to change as the fuel is to be burned in the combustion chamber. The last is with the internal combustion, the mass flow rate entering into the turbine blades is greater than at the compressor because the fuel is heated in the combustion chamber. So we are going to neglect this. So these are the losses at every point where we need to take into account. Okay, the loss of the kinetic energy, the process of the compression and the expansion are assumed to be irreversible. We know that the process is irreversible, and also the fluid friction is going to increase the pressure loss, and the other is because of the increase in the entropy. The we need to add an extra fuel to compensate for the amount of the work consumed by the compressor and the amount of the work delivered by the turbine. And we also know that the Cp and Cv values as well as the gamma values of the air throughout the gas turbine cycle in actual practice are going to change, and also the mass flow rate is not constant. Okay, so we need to account for all these factors when we are going to deal with the practical calculations.